Assalamualaikum and hi, my name is Shami Imani bin Azhar, AD170055, and today I will present about my final year project titled Effects of Reaction Temperature on the Flow Pattern in a Bubble Column Reactor for Biodiesel Production. My supervisor for my final year project is Dr. Nurul Fitrah binti Nasir, and my examiners are Dr. Nomayati binti Nordin and Prof. Maria IRTS Dr. Bukhari bin Mansur. Okay, for the outline of my presentation, it comprises of introduction, literature review, methodology, analysis, and conclusion. Moving on to the introduction. For the background of the study, biodiesel is a form of diesel consisting of long-chain fatty acid monoalkyl esters. It is produced by trans-esterification. Biodiesel is produced through the means of trans-esterification by using biodiesel reactors. And for the study, bubble column reactor is chosen for the process to produce biodiesel. And bubble column reactor is a device used to produce and regulate gas-liquid chemical reactions. The reaction temperature acts as the manipulated variable in the biodiesel production process, and therefore CFD simulation is performed on the bubble column reactor to predict the effects of reaction temperature for the biodiesel production process. There are three problem statements. Firstly, to study whether the temperature factor can maximize the efficiency of biodiesel production in bubble column reactors. And hence, by studying the fluid flow patterns in the trans-esterification process, the information that is necessary for increasing the efficiency of biodiesel can be obtained. And then, by making the reaction temperature, by narrowing the scope from 523 Kelvin to 563 Kelvin, the effects of reaction temperature can be studied. Moving on to the objectives. The main objective of this study is to conduct a simulation of biodiesel production in a bubble column reactor by using various temperatures. The second objective is to predict the effects of various reaction temperature on the flow pattern in a bubble column reactor for trans-esterification process. Next, moving on to the scope of study, the scaled-down bubble column reactor is designed and constructed by using SolidWorks. The bubble column reactor has two obstacles inside them. The obstacles are perforated plate type with 24 holes on them. The model is then imported into a compatible CFD simulation software, and in our case, ANSYS Fluent. The temperature for the reaction is set at 523 to 563 Kelvin, and the inlet velocity is fixed at 2 meters per second. The simulation is conducted by applying the desired boundary conditions. The results are then compared for the aim of validation. Literature review. Okay, firstly, I will talk about biodiesel. Biodiesel is defined as a fuel comprised of monoalkyl esters of long-chain fatty acid derived from vegetable oils or animal fats, designated P100. Some of the notable properties of biodiesel includes high oxygen content, high molecular weight, high density and viscosity, good lubricating properties, and high setting numbers. Next, the bubble column reactor. Simply said, the bubble column reactor is a cylindrical vessel with a gas distributor at the bottom. The gas is pushed via a distributor in the form of bubbles into either liquid phase or a liquid solid suspension. It can be used for conducting a variety of two-phase and three-phase reaction. Bubble column reactors possess flexibility in their residence time, excellent heat and mass transfer characteristic. BCR has excellent heat and mass transfer characteristics, require little maintenance, low operating costs, and lack of moving mechanical parts. And next, I will talk about computational fluid dynamics, or also known as CFD. CFD can analyze and solve problems that involve fluid flows, and with this statement, we can use it to achieve the objective. The CFD analysis uses numerical analysis and data structures to perform calculations. Therefore, it can fabricate the simulation of the fluid flow along with its interactions and constraints. The software, which is ANSYS Fluent, contains broad physical modeling capabilities needed to model flow turbulence, heat transfer, and reactions for industrial applications. The software covers an extensive range and spatial models. These advantages are highly important as the software can meet the criteria of the bubble column reactor that we are using in this study. Next, for the methodology, shown here is the flowchart of the process of the whole study, and then this is the geometry model of the bubble column reactor. As you can see, this is the design that we have used for the simulation, and some of the main parts of the bubble column reactor includes outlet pipe, wall, and inlet. And we have two different designs that we have used in the simulation. As you can see on the top right side is design 1 and design 2. The notable difference between them is the perforated plate that acts as the obstacle inside them. Next, moving on to the meshing. Meshing is a process where grid formation is generated on the geometry. The process allows the software to run calculation based on the domain. And as we can see on the top right side, it shows the meshing, the fluid flow window, the fluent window to be exact. And upon importing the geometry, we can proceed to the meshing. And in the meshing window, we can create name selections, and in our case, inlet, wall, and outlet. And then we apply phase sizing to the critical parts of the meshing. And there are the 5 different parts that we have applied with the phase sizing. And as you can see on the top right side, these are the locations of the phase sizing. And phase sizing is applied to reduce the skewness and the orthogonal quality of the meshing, so that the meshing can perform better to gain better calculation results. And also we perform grid independent tests. Grid independent test is the process that we use to improve the result of the simulation calculation. And to do this, we enable the adaptive sizing and mesh diffuturing feature on the mesh settings. Therefore, we manipulate the span angle center and the smoothing so that a different series of mesh can be generated. And then we choose the meshing with the best skewness and orthogonal quality to perform the simulation. Next, moving on to the solution setup. So solution setup is the final step in solving a multi-phase flow problem, and both design 1 and design 2 will have the same solution setup and the same parameters, and the general parameters such as the models, the materials, the cell zone condition, and the boundary conditions can be determined according to our desire. And as for the boundary condition, the table on the right shows the boundary condition that we have applied in the study, in the simulation, and it is really compulsory for the solution to run the simulation. And as you can see on the left bottom side, it shows the scale residuals graph, which is usually visible when computing the simulation. Next, as for the analysis, there are 5 different results that we can obtain from the simulation. This includes the flow pattern, the volume fraction, and the velocity magnitude. Also, there are velocity vectors and also the streamline. First, I will talk about the flow pattern. The flow pattern of a multi-phase fluid system is the geometrical distribution of each individual phase that exists inside the fluid domain. And as we can see, there are three flow patterns, which signifies that the three different reaction temperature that we use for the simulation. And The flow pattern emphasizes the flow conditions and regulates the flow parameters that related to the simulation. And as we can see, the vapor volume fraction for this simulation, which is in design 1, varies with the increasing of the temperature. Similar to design 1, the design 2 uh, vapor volume fraction also shows similar characteristic, which the higher temperature shows the higher vapor volume fraction. And at the tip of the outlet, of course, the vapor volume fraction is high as the methanol vapor exiting the bubble column is significantly high. Next, moving on to the velocity analysis. The velocity analysis includes the velocity contours and the velocity vectors. As I have said before, the velocity at the inlet is set at 2 meter per second. And firstly, I will review about the velocity contours. The velocity contours shows the magnitude of the velocity that occurred inside the bubble column reactor. And similar with the flow pattern, higher reaction temperature yields higher velocity magnitude. And then about the velocity vector, the velocity vector shows the vector or direction of the fluid that occurred inside the bubble column reactor. And this, if we perform better analysis or zoom into the picture, the the vectors around the plates are kind of swirling, which signifies the existence of turbulence flow inside the bubble column reactor. Next, to perform better analysis, I have plotted graphs of the velocity against the distance. So as we can see, these are the graphs for both design 1 and design 2. And overall, the velocity increases over the distance inside the bubble column reactor. And the highest the higher the highest reaction temperature, which is 563 Kelvin, shows the highest velocity magnitude for both designs. Next, moving on to the gas holdup. In summary, gas holdup is the basic parameter that indicates the hydrodynamic characteristic of a bubble column reactor. It is required to determine the effect of temperature towards the reaction rate and the flow pattern. The reaction temperature affects the gas holdup in the bubble column reactor. As we can see from the graph, the highest temperature, which is 563 Kelvin, shows the highest curve compared to the 533 Kelvin and 543 Kelvin. And with the increase of the reaction temperature, the gas holdup will also increase. Next, we have reached the conclusion. Firstly, the effects of the three different temperatures towards the hydrodynamics behavior and the fluid flow in the bubble column reactor for the biodiesel production were investigated, and the fluid flow inside the bubble column reactors has been successfully simulated and evaluated by using the ASYS software. And by using the approach of CFD, the analysis of the complex fluid flow problem can be done with minimal effort and cost. And as for the setup, we have used volume of fluid model for the multi-phase model, and for the turbulence model, we choose the RNG K epsilon in order to forecast the pattern of the turbulence flow inside the bubble column reactor during the process. And also, we perform the validations. The results from the previous research and this research comprises of several differences, as the past research does not include the utilization of the perforated plate in the bubble column. This can explain the reason why the, the the results are quite different, and therefore it is validated. And lastly, as for the recommendation, like the first recommendation is that I suggest that we can perform other modifications on the design for the geometry models, such as installing other shapes of obstacles, other types such as the parallel plates. Also, we can change the shape of the bubble collaborator. And second, we can consider using other multi-phase model and setup for the competition of the analysis. And we can use mixture as the multi-phase model, or also we can use K omega for the turbulence model. And the third one, we can substitute the working fluid with an alternative working fluid, because in the study we use triolene as the target slide. Maybe we can substitute other kinds of fluid to better suit the simulation. And lastly, we can use computers with higher specification, as the computation of the CFD analysis is very time taking. And maybe we can maybe we by using better computers with higher specification, the waiting time, the computation time can be reduced, therefore we can perform more simulations. And I guess that is all from me. Thank you.